Allylic bromination of methylenecyclohexane would be expected to give two isomeric monobromination products. Identify the other isomer. First of all, what we can see here is our reagent is NPS, and what NPS does is it's a radical reaction that places bromine on the allylic position. They actually gave a hint in this question. They wrote allylic bromination, so they already told you that's what you're supposed to get, and you can also see it in the product. What does allylic mean? When we have a double bond, the carbon next to the double bond, that's an allylic carbon. So NPS adds bromine to the carbon that is one carbon away from the double bond. For example, we have a double bond here, so these two positions are allylic. Since our molecule is symmetrical, they're exactly the same. So if we could place bromine on either side, it would give us the same product. And that's what we see here. We see bromine on the allylic position from the double bond. Now, what could be the isomer? What can be the other molecule, the other product that is created from this reaction? And in order for us to figure out the other product, we have to look into mechanism slightly. So, in the mechanism for NPS, we have initiation, propagation, and termination steps because it's a radical mechanism. And initiation basically will produce a bromine radical. So we're going to show our bromine radical. That's what initiation produces. I did not show the steps, but initiation using NPS will produce a bromine radical. And the most important steps for us are propagation steps, because they will allow us to figure out who this mysterious isomer is, who is the second product. So what we're going to do after initiation has created propagation, has created the bromine radical, we will do the propagation steps. First, what we do is we start with our molecule and we react it with Br radical. And we know that this is the place where bromine wants to attach to. But what will happen is this carbon has 4 bonds. It's connected to 2 carbons and 2 hydrogens. So we will have to take away one of its hydrogens so that the bromine could add to it. So I'm going to show this hydrogen. And the way we draw radical arrows, they're unlike other arrows. We draw them basically one way, representing a movement of 1 electron. So when a bond breaks, it looks like a fountain. So we will draw 1 electron going to the hydrogen, 1 electron going to this carbon, and the bromine gets together with the hydrogen. And what we create is this kind of radical. So the electron went to the carbon, so there is an electron here now, and hydrogen got together with bromine to make HBr. So this is our radical intermediate. Now this radical intermediate, notice this radical is in a allylic position. It's on the carbon next to the double bond, like we predicted it would be. And eventually bromine will add to it, and that's how I get this product. So what other product could I get? If you look at this radical intermediate carefully, we might notice that it is capable of a resonance. Just like a carbocation, if we have a carbocation next to a double bond, we can do resonance like this. If we have a radical next to a double bond, it is also capable of resonance. So let's go ahead and show the resonance. What we can do is this double bond can break and it can get together with the radical to place a double bond here. And now this carbon got its own single electron, so now the radical is on this carbon. So again, let me show it even more clearly. Let me redraw it here. We have noticed that we would have a radical on the allylic carbon in this mechanism, and this radical is next to a double bond. So what we can do with the resonance is we can break this double bond like a fountain. You draw it like a fountain. And one electron will go to this carbon at the end, and another can get together with this electron to form the new double bond. And so my new double bond will be here and my radical will be here. That is the place where bromine will be able to be added to create the other product. So the other product could come from the fact that the intermediate radical in the mechanism can be resonance stabilized, can have a resonance, and from this resonance we can make a different product. So our bromine could add to this carbon, to this new allylic carbon, and my double bond would be inside the ring right next to the methyl group. So let's go ahead and look at the options here. So basically my product would look like this. And so let's look at the options to see where I see. First of all, we can eliminate B and A because here bromine added to the ring, and we can see that it's adding to the methyl group outside of the ring. And looking at C and D, we can see that D is the correct answer because we have double single bromine. Double single bromine. Here we have double single bromine, so we can eliminate C as well. And the correct answer for this question should be D. Again, the reason we figured out that it was D was because we had to do a little bit of mechanism to do this question, and we have figured out that where this bromine is in the product, that used to be the radical, and then we realized that the radical could do a resonance, so we did the resonance, and that allowed us to figure out the second product possible for this reaction. This is Maya from Transformation Tutoring. I really hope that you found this video helpful, and I look forward to seeing you in more of my organic chemistry and general chemistry videos.